At Rescue Education, we have the best explanation every time. I'm Dr. B, and I'm going to help you easily and rapidly learn organic chemistry. If you like the video, you'll love my book. Learn more about it at rescueedu.com or hear more about it at the end of the video. The second semester book comes out in fall 2020. Today, we're going to talk about Lewis bonding and formal charge in organic molecules. It's extremely important to know bonding and charge so well that they become second nature. First, we'll quickly review Lewis dot structures and simple Lewis bonding. Here's an overview of how Lewis bonding works. In atoms, the electrons are arranged in shells. The first shell holds 2 electrons. The second shell holds up to 8 electrons. The outer shell is called the valence shell and is usually partially filled with electrons. When atoms bond, they only use unpaired valence electrons. Bonding occurs to give each atom a full valence shell. The octet rule says atoms in the second row, carbon, nitrogen, oxygen, and fluorine, bond to get 8 electrons. Bonding can be either ionic or covalent. Let's start from the atoms. There are very few elements you need to know in intro organic chemistry. The essential ones are circled. Carbon and hydrogen are the most important because they occur in virtually every organic molecule. The group number of the atom shows you how many valence electrons the atom has. Hydrogen has only 1 electron. It is in group 1 and has 1 valence electron. Carbon has 6 electrons in total. It's in group 4, and so it has 4 valence electrons. The first representation of the electronic configuration of carbon shows all of the electrons. Carbon has 2 electrons in the first shell and 4 electrons in the second shell. The second shell can hold 8 electrons, but it is only partially full. The second representation is the Lewis dot structure. It shows only the valence electrons. In carbons, these electrons are all unpaired. Unpaired electrons are used to make bonds. We can draw these two types of representations for other important atoms. Hydrogen is in group 1 and has only 1 valence electron ready to bond. Nitrogen is in group 5 and has 5 valence electrons. In the Lewis dot structure, they occur in 1 lone pair and 3 unpaired electrons, ready to make 3 bonds. Oxygen is in group 6 and has 6 valence electrons. These occur as 2 lone pairs and 2 unpaired electrons, which can make 2 bonds. Chlorine is in group 7 and has 7 valence electrons. It has only 1 unpaired electron, which can make 1 bond. It's important to know these patterns. Atoms are unstable and bond to achieve a full valence shell. Full valence shells can be achieved by ionic or covalent bonding. The type which occurs depends on the relative electronegativity of the atoms involved. The electronegativity of an atom is its ability to stabilize electrons. It increases from left to right and bottom to top. It's important to realize that hydrogen is only slightly less electronegative than carbon, and for many purposes is considered to be of about equal electronegativity. Ionic bonding occurs between 2 atoms of greatly different electronegativity. Electrons are formally transferred, so each atom gets a full outer shell of electrons and is stabilized. The more electronegative atom gains an electron, and the less electronegative atom loses one. In the formation of lithium fluoride, highly electronegative fluorine gains an electron, and highly electropositive lithium loses an electron. Each atom is left with a full valence shell. In this case, the ions form a high-melting crystalline lattice. Organic molecules occasionally have ionic bonding. When it occurs, it can greatly affect reactivity. Covalent bonding happens when two atoms of similar electronegativity share electrons to get full valence shells. The two bonding electrons reside more or less midway between the atoms. The vast majority of bonds in organic compounds are CC and CH bonds, which are always covalent because carbon and hydrogen have almost identical electronegativity. Methane is the simplest organic compound. It can be viewed as one carbon atom sharing its 4 unpaired electrons with 4 hydrogen atoms. The result is carbon gets a full octet in its second shell, and each hydrogen gets a full first shell. All the atoms are stabilized. The bonds are purely covalent. It is awkward to draw Lewis dot structures, so we will start using Lewis structures in which each bonding electron pair is represented by a line. I want to mention that in reality, bonding can be anywhere on a continuum between purely ionic and purely covalent. Oxygen, nitrogen, and the halogen atoms, such as chlorine, can also use their unpaired electrons to make covalent bonds. The non-bonding lone pairs are left untouched. Oxygen can form 2 bonds to hydrogen because it has 2 unpaired electrons. This gives oxygen a full octet. Nitrogen forms 3 bonds because it has 3 unpaired electrons, and chlorine forms 1 bond. There are many ways to draw Lewis structures for these molecules. It's permissible in many instances to leave off the lone pairs. They are still understood to be there. Geometry is not important, so it's usually fine to draw a molecule such as water either in a linear or bent geometry. In carbon-carbon single bonds, each carbon contributes 1 electron to the bond. Ethane is the simplest molecule with this bond. The rest of each carbon's octet is completed by forming 3 carbon-hydrogen bonds. In carbon-carbon double bonds, each carbon contributes 2 electrons to the bonds. There is a total of 4 electrons shared in the double bond. In the molecule ethylene, the simplest molecule with this bond, the rest of each carbon's octet is completed by forming 2 carbon-hydrogen bonds. The Lewis structure is usually drawn with this geometry to reflect the real geometry. Carbon-carbon triple bonds, such as the one in acetylene, result in the carbon sharing 6 electrons in total. Acetylene has 2 hydrogens to complete each carbon's octet. Other atoms, such as nitrogen and oxygen, can also participate in double and triple bonds. Molecular nitrogen must have a triple bond to acquire a full octet for each nitrogen, and molecular oxygen must have a double bond. Sulfur, phosphorus, and boron can violate the octet rule. The sulfur in hydrogen sulfide does follow the octet rule and has 8 electrons in total. 4 in the non-bonding pairs and 4 in the SH bonds. But sulfur in sulfuric acid has 12 valence electrons and is said to be hypervalent. Likewise, phosphorus in phosphoric acid has 10 valence electrons and is also hypervalent. The boron atom is in group 3 and has only 3 valence electrons. It can form 3 bonds with 6 valence electrons when it is neutral. But a neutral boron in a molecule can accept 2 more electrons from an atom such as a fluoride. This means boron has achieved a full octet, but it also means that it is negatively charged. Now let's look at formal charge in organic molecules. Sometimes individual atoms in organic molecules will have a formal charge. The vast majority of atoms in organic molecules are neutral, but it's important to know when a particular atom is charged, because this is often a place of reactivity. A charged atom will have a counterion, but we will usually ignore it. The formal charge on an atom can be calculated using this formula. You are subtracting the amount of electrons the atom in the molecule owns from the amount of electrons that the free atom owns. The atom in the molecule owns half of the bonding electrons, but all of the non-bonding electrons. As an example, let's calculate the formal charge of each atom in the molecule NH4. Atomic hydrogen owns only one electron. The hydrogen in NH4 owns half of two bonding electrons, which means one electron also. Hydrogen is neutral. Bonded hydrogen is always neutral, so we don't need to do this calculation again. Atomic nitrogen owns 5 electrons. The nitrogen in NH4 owns half of the 8 bonding electrons, which is 4, and there are no non-bonding electrons, so the net charge is +1. We can also calculate the overall net charge of the molecule. We add up all the charges of the individual atoms. The net charge of the entire molecule is +1, since all of the hydrogens are neutral and nitrogen has a +1 charge. In organic chemistry, we always put the charge right by the atom where it resides. This is the ammonium ion. Pause and give these sample problems a try. For the following molecules, calculate the formal charge on each central atom. Draw a clear representation of the molecule with the charge where it resides. In A, the number of electrons in the free carbon atom is 4. We subtract half of the 6 electrons in the 3 bonds. This is 3 electrons. Finally, we subtract the 2 non-bonding electrons. The charge on carbon is -1. Put the negative charge right next to the carbon. This is an example of a carbanion. In B, the number of electrons in the free oxygen atom is 6. We subtract half of 6 electrons in the bonds. This is 3 electrons. Then we subtract 2 non-bonding electrons. The charge on oxygen is +1. This is a hydronium. Notice that the pattern of bonds and non-bonding electrons is the same in A and B, but the charges are very different because the atom is changed. In C, the number of electrons in a free carbon atom is 4. We subtract half of 6 electrons in the bonds. There are no non-bonding electrons. The net charge on carbon is +1. This is an example of a carbocation. It is very important to know by heart all the formal charge patterns for carbon, oxygen, nitrogen, and the halogens. For simplicity's sake, we have made all of the bonds to hydrogen, but there could be any reasonable group or atom bonded instead. The most important part is the middle column, which shows you the pattern for the neutral atoms. Know these automatically. Neutral carbon always has 4 bonds. Neutral oxygen always has 2 bonds and 2 lone pairs. Neutral nitrogen has 3 bonds and 1 lone pair. And a neutral halogen has 1 bond and 3 lone pairs. All of these atoms can be positively charged. A positively charged carbon will always have 3 bonds and no non-bonding electrons. A positively charged oxygen will always have 3 bonds and 1 lone pair. You can do the formal charge calculations if you want, but ultimately you have to know these patterns automatically. The negatively charged versions of each atom all have at least 1 lone pair. The only atom that has fewer than a full octet is the carbocation. It has 6 electrons. All the other atoms have 8 electrons. Oxygen, nitrogen, and the halogens are electronegative and want to have their full complement of 8 electrons. Next, notice that the generic symbol for the halogens is X. When we don't need to specify a particular halogen, we will label it X. This is used a lot in organic chemistry. The last point is that charged atoms are usually unstable and reactive. If you see a charged atom in a molecule, consider that it is likely the location of reactivity. Since carbon is the most important atom in organic chemistry, it's essential you know its different forms and their reactivity. Recall that a carbon with 4 bonds is always neutral, whether it is in a single, double, or triple bond. A carbocation always has 3 bonds and no lone pairs. It is very reactive because it has only 6 electrons and wants a full octet. Theoretically, a carbocation can be on a single, double, or triple bonded carbon, but the last 2 forms are extremely rare and you should not use them. A carbanion always has 3 bonds and 1 lone pair of electrons. It will be found on single, double, and triple bonded carbons. Carbanions are reactive because they want to get rid of the negative charge. It is often okay not to draw the lone pair, although it is still understood to be there. There are 2 other forms of neutral but very reactive carbon. The carbon radical has 7 valence electrons and is reactive because it would like its full octet. The carbene has 6 electrons in the form of 2 bonds and 1 lone pair. It is also very reactive because it would like to achieve its octet. Finally, it is important to never, ever draw a carbon with more than 4 bonds. A carbon with 5 bonds is called a pentavalent carbon and is not possible because it has 10 electrons and violates the octet rule. A carbon with 5 or more bonds is sometimes called a Texas carbon. Drawing it will result in serious points taken off on exams and assignments. Finally, we look at drawing reasonable organic structures if you are given a molecular formula. This is an excellent exercise to help you internalize the correct bonding in organic molecules. There is a logical way to approach these problems. Let's look at deriving the structure of bicarbonate using this set of rules. The first step is to list the Lewis dot structures of all of the neutral atoms and then add or subtract electrons if there is an overall charge. We make a list with 1 carbon, 3 oxygens, 1 hydrogen, and 1 extra electron. The second step is to bond all the atoms together except for hydrogen. Never make oxygen-oxygen bonds. They are too unstable. There may be more than one way to do this. For bicarbonate, we draw carbon as the central atom and bond all of the oxygens to it. At this point, carbon and the oxygens all have 7 electrons each. In the third step, add the hydrogens and add any extra electron or subtract if there's a positive charge. In this step, try to add the electrons to the most electronegative atoms. For bicarbonate, we add the hydrogen to 1 oxygen and an electron to another. In the fourth step, push electrons around to get complete octets. Don't add or subtract new electrons. If you must leave an atom with an incomplete octet, make sure it's carbon. Oxygen and nitrogen are very electronegative and have to have complete octets. In bicarbonate, we push 2 electrons together and all atoms except hydrogen have complete octets. The last structure is not reasonable. If you bond the hydrogen to carbon, then there is no way to move electrons around to give complete octets for the oxygens. Try it. Pause and do these sample problems. Draw the best Lewis structure that corresponds to the molecular formula shown. Show all non-bonding electrons and formal charges. In A, we have 1 carbon atom, 1 oxygen atom, and 2 hydrogen atoms. First, connect the carbon and oxygen atoms. Carbon has 3 unpaired electrons, so it's smart to put the 2 hydrogens here. Then both carbon and oxygen still have single electrons. Push them together to form a double bond. In B, we have a carbon atom, a nitrogen atom, and a single electron. Bond the two atoms and push together electrons 2 times to make a triple bond. Carbon is left with only 7 electrons, so give it the extra electron to complete its octet. Put the negative charge right beside the carbon. If you're using my book, I encourage you to do the extra test your knowledge problems for this topic, so you can be sure you really understand it. All the answers are at the back. This video is closely based on my first semester organic chemistry self-help book. The book is organized into standalone topics so you can quickly teach yourself a few troublesome topics. It's also logical and organized from beginning to end, so you can easily learn the whole semester if you need to. My self-help book is particularly valuable in difficult learning situations, but you can also use it to get an edge. If you want to learn more about my books and videos, how to get the books, or my future projects, go to rescueedu.com.